Hello.
Hello there.
Let me see what else I've got here. Just want to see if there are other ring closure examples. I guess. All right. I guess in problems test 3, I've got something here. Okay, so we're going to look at the ring closures today. There we go. So I'll use this one as an example. Now I know we've got esters here, but it doesn't really matter what functional group there is, as long as it's a carboxylic acid or carboxylic acid kind of derivative here that can possibly form a lactone. All right, let's look at what we've got. Okay, so a student had raised a question the other day about how you can tell which OH is going to interact with which carboxylic acid grouping. Now, the idea here is that we know that the reaction of the lactone, and I went through this at the end of the last class here, was between something that I'll make it an OH, but I know this is OMe. Like I said, it doesn't really matter. But effectively, what we're looking at here is this kind of arrangement. I mean, that's the net effect of everything. So it's really this O here joining with the C double bond O on the other side. So in this situation, we're looking at what I'm calling a separated ring system, because what's happening is that the OHs that are closest to the carboxylic acid groups are the ones that are doing the business here. So what I'm going to do is, again, I'm just going to, I'm not going to actually show the whole ring here. I think it might be easier just to show what's going on here. I'm not showing the whole thing, just to showing a sort of a more schematic diagram, if you will. And you can see that if we take the OHs that are closest to each of them, the net effect is something that looks like this. And the point being that you're going to end up getting this kind of joining point between these two separated rings. Now that happens if you take the OHs that are closest. What happens if we do the reverse and we have the OHs from the other side? So I'm just going to do the same thing here. And you might be wondering, well, how are you going to know which way it's going? Well, the thing is that you'll always have the product. So you'll always know what the situation is going to be. So what's happening here is I'm going to take the OH and take each OH with the one that is further away from it. So we end up getting this situation. No, I can't do that. And you can see the difference between the two situations. Now, instead of two separated rings, I would say you have two fused rings. So it's fused. And this one is, I'd say, separated, if you will. Hopefully you can see the difference between the two. Does anybody have any questions?
Yeah, I do. So on the exam, you're going to show the result and we just have to show the mechanisms.
That's
So
right.
like if it's closer or if it's farther away, that's how you'll know if it's...
That's how you'll know. That's exactly right. Yeah.
Okay, so I was just wondering. Thank you.
Yeah. And what I'm not going to do is just give you the reactant and say, well, what's the product, right? And the mechanism. No. I'll give you the reactant and the product, and you'll come up with the mechanism from there. All right, so that's the main intro part that I'm trying to show you here. But if you take the OHs that are closest to each of the carboxylic groups, then you're going to end up with a separated system. And if you take the ones that are furthest away from each one, you'll end up with a fused system. And you'll know which one you're getting because you'll have it in front of you. So let's take a look. Does anybody have any questions?
Yeah, I do.
Yeah.
Well, I was looking at the one that you started showing us that was at the top. It's really hard for me to really see what you're doing with the way that you drew it. I guess I'm just too literal. But I was interested in seeing, it had the answer that looked like it was a separated ring. And I was interested in seeing what it would look like if it was a fused ring.
Well, I did that. That's what I just did.
Well, I know you did it in that scribbly way, but I can't really tell.
You don't like the scribbles.
I do not like the scribbles.
Okay. Well,
because I was looking at the answer that you had that was printed, that was nice and neat and not scribbled.
Let me see. I thought I had.
The one at the top.
Yeah.
That was.
Oh yeah. Okay. So you'd want to know what it actually looked like. All right.
If it was fused.
Okay. So I don't do that on the following page, do I? I guess I just give you a separate example. Or did I? No, I did.
It's the same one?
It's the same one, Sunshine.
Okay, well then I'm good.
There you go. There he is, right there.
Okay,
right there.
I'm good.
Yeah, I think so. All right. Okay, so let's look at how this affects the mechanism here. And one thing that you can do is once you figure out which OH is interacting with which group, and we know again, since this is separated, that the OH that's closest to each is the one that's going to react, then we can go ahead and number these. And that's what I've done is I've numbered these 1, 2, 3, 4, 5, 6, so that I could get an idea of the size of the rings that I was going to get in each instance. Then I can do the same thing, A, B, C, D, E, F. Now notice I've numbered between the O from the OH and the C from the C double bond O. numbered or lettered. And that's what's enabled me to determine how big the rings are in each instance. And as you can see, we get two 6-membered rings here. Does anybody have any questions about that part? Do you have to number them? No, you don't. I'm just doing this for kicks, just to give you an idea about how you can tell how big the rings are going to be. In the case of the fused ring, I've done the same thing, but again, because it's fused, and I know it's fused, then I've taken the OH that's further away and I've numbered from the O, from the OH, again over to the C double bond O. And you can see that's going to be G, which is 7. And same with the OH over here, which is 7. So we know we're going to get two 7-membered rings that are fused together, have a common bond here. Does anybody have any questions? So that's not a bad technique in order to make sure that you are indeed getting the right products. All right, let's take a squiz. Oh, well, let me do a little bit of do a little poll here. All right. So how do you feel about not so much the mechanism, but just about the separate rings and the fused rings? That's really where my focus is right now. So please go ahead and answer this. I'll give you another 5, 4, 3, 2, 1. I've still got 4 people who have no, just one person hasn't voted. All right. Okay. Anybody have any questions? Anybody have any questions that could help them?
I get the gist. The further, if it connects with the one that's further away, they're fused, and if they're closer, they're separate.
That's right.
Yes, I get it. I just wanted to see more examples.
Oh, we will. We
Okay.
will. Yeah. Yeah. So let's take a look at some test questions. Oh, so we lost somebody. Sorry to hear that. All right. So let's take a look. This is question 2 on the test here. There we go. That's probably not a great example because this is symmetric and there really is no difference either way. Not really.
Well, one ring is bigger than the other, right?
True. Man, you can count them and you can see that it does, because they're symmetric. There's no way of doing it any differently than what we've got here. So
Gotcha. Now, and I apologize, I'm a little bit behind, so I'm still catching up. But just from what I've seen from those last 2 problems, I've not watched this video yet, so forgive me. Basically, the C double bond O, anything beyond the C double bond O is going to link up with the proton and create, in this case, water. In the last case, it was the
well, to be clearer, it's the O joining with the C double bond O, forming H2O. So this O will join with this C double bond O, and this O will join with this C double bond O.
Okay.
All right.
But yeah, okay, I got you.
All right. I'm going to close that one down. Let's look at the next one. See if that one's any better. I want something a little bit more prescriptive.
So I have a question. So
Yeah.
it means anytime there's a carboxylic acid and an alcohol group, they'll always fuse if they have that.
Yeah. Yeah.
Right?
They sure will. This is a better example. This one's a better example. Okay. All right, just for kicks, just for kicks, okay? Now, this is only for kicks. I swear, only for kicks. What am I going to do? Can anybody tell me? Can anybody predict? See how well you know me. What am I going to do? Just for kicks. No? Nobody can predict?
Are you going to letter and number them?
Nope.
Oh, well,
Not going to do that. I'm going to show you what it looks like if it wasn't fused. All right? So let's see. If it wasn't fused, this would be the product. I think that's right. 1, 2, 3, 4, 5. Yeah. There we go. So that's what it would look like if the OHs that were closest to each of them joined to each C double bond O. So if this OH joined to this C double bond O, if this OH joined to this C double bond O, that's what you get. But that's clearly not what we have. So we know it's not that situation. So what's going on here is this. Just ignore this. We don't need that. Just going to draw this the same way. So what's going on here is that the O is joining to this C double bond O, and this O is joining to the other C double bond O. In dotted lines, I'll show you the other one. See the difference?
Can I ask a question?
Yeah.
I know I've asked this before, and I'm going to ask you this again because I guess I still don't get it. So there are 4 OHs on that structure.
Yes.
Tell me again how I know that the OHs that are sticking off the C double bond O's don't do anything?
Because they're the leaving group, Julie.
Okay.
They're the things that end up being replaced. They can't be attacking if they're leaving.
Okay. I just needed to hear it again.
Okay.
Thank you.
I'll say it as often as you want.
I just wanted to hear it one more time why.
So on the test, do you want us to add in the water molecule too?
Well, you don't have to do that. I mean, just have to show you have to show the mechanism. The water molecules will be part of the mechanism, Anna.
I just wanted to make sure that I know I'm a very forgetful person when it comes to adding things onto the test. So I know knowing.
Well, it's not about adding anything on. It's about making sure that everything gets taken account of, Anna.
Yeah.
All right, so I'm going to go ahead and do this example here and show you exactly what is going to be required. Right, is everybody okay with how I know which OH is reacting with which C double bond O? Let's do a poll here and find out. Is everybody okay with at least how I know which OH is attacking which C double bond O? Okay, I'll give you another 5, 4, 3, 2, 1, 1. There we go. Okay. So there you go. So anybody has any questions here that can help them? Okay.
Will you number like how you did on
Oh,
other
sure,
example?
sure, I will, but not right now. Let me get to the point
Okay,
where we're
thank you.
going to do the ring closure, and then I'll do the numbering, okay? So in the first step, the H plus joins onto the C double bond O. Now, it doesn't matter which one. No, it doesn't. I mean, you'll have to do both eventually, but it doesn't matter which one you choose to do first. All right, I'm going to relent here a little bit just because it does bother me that 4 people halfway understood. So I'm just going to put this little other diagram down here. Don't do this to me. There we go. All right. I want to see if I can shrink it a bit. There we go. It's better. Just going to put a little mini diagram underneath here. Hopefully it'll clear things up a bit. All right. There we go. That's what I wanted. All right. So I'm just going to redraw this. I'm kind of doing it in a smaller space here, but I don't need the whole thing. So again, this OH is attacking here and the other OH is attacking here. And I'll put the little dotted lines in for the other possibility if it didn't happen. That would form a separated ring system. So the dotted arrows there form the separated ring, and this one forms the fused ring that we have here as the product. Okay, I hope that clears things up, having that right there as well. Okay. So now we know what's going to attack what. Now we know that this OH, see this one here that I'm pointing to. Can you all see my cursor? Can you see my cursor?
Yes, we can see.
Yeah, good. Okay. Now I'm going to go ahead and number this ring because that's the one we're working with. So 1, 2, 3, 4. So I know I'm going to get a 4-membered ring out of this. So it's going to be this O that's going to attack that C+. So now I'm going to look at the effect of that. And if we look at what that arrow did, all it did was form that bond between the O and the C+, which turned that O into an O+. And the rest of it is just going to be the same as what it was. Okay, going to stop here for a second. Does anybody have any questions about that ring closure step? All right, let's gauge your understanding of the ring closure step.
Could you do it one more time? Just go over it before you take the poll.
Okay. Tell me a specific question that would help here.
Okay, so I'm trying to draw them as you're going.
Yeah.
Where do you start with? I mean,
I'm not understanding the question, Mario.
Okay, I didn't see where did you start it with when you were trying to, after you numbered them, you were trying to draw the ring. Did you go with, did you just count 4-member and then you draw a 4-membered ring, which on one corner there's oxygen like that? Yeah,
like 1, 2, 3, 4. So the numbering still matches.
Okay. All right. Thank you.
Okay. All right. Let me get an idea of people's understanding of this. So just that ring closure step. That's what I'm interested in. Tell me what you think. The ring closure step. Just the ring closure step, please. not the rest of it, just a ring closure. Okay, 5 more seconds. 4, 3, 2, 1. Okay, so 18 versus 4. All right, any questions that could help out here?
I just want to be clear. So the OH number 1 is going where that positive sign is, right?
Yes, well, that's what's going to join together. Yes, that's what the arrow is telling us. That's the story the arrow is telling us, Diana. Yeah.
Okay.
So you'll notice that that 4 still has the 2 OHs attached to it, right?
Right.
And the rest of it is just pretty much stayed the way it was. And I know how big that ring is because I know I counted 1 through 4, so I know it's a 4-membered ring. All right, the next step is a proton transfer, and in essence, it doesn't matter which. Whoops. Try that again. It doesn't matter which of these OHs takes it, and it's a proton transfer. So what we end up with is this. I'm going to try and be a little bit smart about this and separate out the OH on the other one. Now you might be wondering, well, how do you know that this happens? Well, we know this happens because this OH, dual OH grouping is what becomes the C double bond O, this business down here. That's what's going to form the C double bond O. So I know that this one of these OHs has to leave. And if I want to make an OH leave, what I do is I protonate it. And I get that proton from the O that was the OH. Oops. There we go. And everything else stays the same. Does anybody have any questions about this one? Okay, the last step there in this ring closure is the water leaving. And Anna, you were asking this before. The water would be shown, one of the waters anyway, would be shown in this step. Okay. And that's what we have so far. Does anybody have any questions? Okay. A bit nervous about this, but I'll ask. How do you feel about the mechanism for the first ring closure, the complete mechanism? We're not done yet, but the first ring closure, tell me how you feel about the mechanism. Okay, 5, 4, 3, 2, 1. All right, so it's about 1/3 to 2/3. That's kind of what I was expecting at this point. For the rest of you who don't understand at this point, or you halfway understand, then what you're going to have to do is practice this. Practice it again and again and again. Just write. There is no substitute for this than putting pen to paper and then just doing it again and again and again. Some people have told me, oh, Dr. Musgrave, I love flashcards. I'm just going to make up flashcards and look at them. Nope, ain't going to work. Flashcards are the way to failure. They are. Flashcards are the way to failure. The only way that you'll get what you need out of this is to put pen to paper and just continue to do it until you hear angels sing.
I totally agree with you,
Thank you, Julie.
Yeah.
because I couldn't do it
The
at all.
last.
This is
No,
so-
I agree.
Donna,
I'm sorry.
you
I do have a question. Easy question. So basically, once the H2O is off on its own and it's having a great day, the last product that you have there, you're generating yet another proton, and that's basically just regenerating the acid catalyst, right?
It is. That's right. And we can use that very proton in the next step to start the next cyclization.
Okay, perfect. Thank you.
Which is a great segue to continue
You're
on
welcome.
here. And Donna, I was hoping you weren't going to disagree with me about writing stuff down. That was good. I'm glad you didn't. About putting pen to paper. That's good.
Oh gosh, no. I'm all about that.
All right. So pen to paper. That's the only way. Look, just looking at stuff is not going to get you anywhere. I guarantee it. I'll say it again. I'm going to be real clear about this. Flashcards are on the road to failure. Flashcard equals failure. I'll say it one more time. Flashcards equal failure.
Dr. Musgrave.
Yes, Courtney.
I have a quick question just to like double check. So the OH that gets protonated is the one that did not start out as a double bond, correct?
It is generally speaking, but in this instance and in the instance of any test question that you'll be given, it won't matter because you have two OH groups there. But you are correct. Technically speaking, it would be the OH that was not on the C double, not from the C double bond O that would get the proton. Yes.
Right. Okay. Thank you.
All right. Any other questions? Okay. So do you have to do this? No, you could get another H plus if you like. I'll do that again. That didn't work out. That's better. All right. So the rest of it is just going to be the same. You know why a lot of people don't like this mechanism? It's because you have to be so organized when you're doing it. You have to be very clear. That's why I love it. It really does require that you are organized about what you're doing. You know exactly what's changing and what's not changing. All right, so looking at the numbering, I'll put numbers on this. 1, 2, 3, 4, 5, and 6. So I know this is a 6-membered ring. It doesn't matter which way you number it, whether you number it from the C plus over to the OH or vice versa. So the next step, again, the 4-membered ring ain't changing. Well, let me do that in a bit nicely. There we go, it's better. A little bit. Okay, so 1, 2, 3, 4, 5, 6. There we go. So I could do the numbering here, and it would be 1, 2, 3, 4, 5, and 6. And the O here, whoops, has a plus on it. All right. Any questions? Yeah.
I think I've figured out a way so it's easier for other people to understand. I was a little confused because in your video, I don't think they counted the oxygen. They started counting the carbons like right after the
Oh,
OH.
I don't know. That wouldn't.
Was
I
it?
don't think that's correct. I don't think
Oh,
I
I
would have
might have
done that.
numbered it wrong myself and when I was doing my notes, and that's what it was. But I
Yeah.
think I get it now, like how to correctly number it and to see which one after you
Right. Yeah. Always number it from what's attacking to what's joining. But it doesn't
Yeah.
matter which way, as long as you do it. It doesn't matter which direction you do it in.
Yeah, I think I got it now. Basically, you start until you get to the double bond, and then that's how you can see if, you know.
And the double bond is always going to be where the two OHs were joined together.
Yes, this is what I was trying to say.
Okay,
Thank you.
good. Okay.
Can I repeat that to make sure I got that right?
Yeah.
The double bond in the end is going to be where the two OHs join together.
Yes. But for the C that joins to the two OHs becomes the C double bond O, to be super clear. And I am going to run out of room, but that's okay because I'm going to actually, I'm just going to say it becomes that product. Well, I'll draw it out. I'll continue it over here on my other screen. Okay, so that leaves, and we end up getting. So this is a continuation. And I'll draw it out bigger because I can. All right. See, that becomes the C double bond O. Do you see that, Julie? I think you were the one who was asking that. There we go. And there we be. So that's how it should look. So that's the entire thing. So you'll notice that the second step is really just a mirror of the first step. Or, it's the same kind of thing, just a little bit different. Does anybody have any questions? Now, when I ask this, I'm just generally trying to get an impression of how you feel about the problem, not that you feel like you could actually do it right now if I threw it in front of you, right? So just how you feel about the problem. Okay, 5, 4, 3, 2, 1. So there you go. So 18 people feel okay about it. 5 people feel sort of okay about it, but not great, I imagine. Okay. So for the rest of you, for everybody, the best thing to do is to practice. Practice, 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 practice. So what have I got here to help with that? The practice part. I think I'll leave this up because I might use it later. So in this test 3 folder, I've got a file called, oh, come on. Don't do this to me. Here we go. I've got a file called More Ring Closure Examples. You can practice on those as well. Let's download that. So there they are. So you can practice those mechanisms, and the answers, well, at least the answers are there for the, but not the mechanism part. I don't know if I've got these. Can anybody tell me if I've got these mechanisms anywhere? I probably don't. But the question that is being posed by this little worksheet here is only just to figure out which OH is reacting with which C double bond O OH. So Julie, this is actually a good one for you because you were concerned about the OHs for the C double bond O's. You know that those are the leaving groups, so those aren't reacting. So for this one, I would want you to see that
It's going to the other side.
yeah, it's going to be the other side. Yeah, and you can count it because you can count the rings. I mean, you can count the size of the rings. You go 1, 2, 3, 4, 5, 6, 7, 8. So you got an 8-membered ring on this side, and on the other side, 1, 2, 3, 4, 5. So we got a fused ring system, 8 and 5. So that gives you an idea. So it doesn't. I don't have a mechanism for these, by the way. I've just got the which OH is interacting with which side. So that might be somewhat useful, at least.
It is. I
Do
think
you
it's,
have examples where they're separated?
No. And I'm going to tell you a secret, but don't tell anybody else, okay?
Okay.
The one you get on the test will be fused.
Okay, perfect.
Don't tell anybody, Donna. I don't want this coming back to me that you've told somebody. All right. Anybody got any other questions? All right, practice, practice, practice.
I think we get the gist of it. It's just practice them out, and probably numbering would probably be the best step to see if you're, using the correct OH, to see starting with the O and then going to the OH and to the double bond.
Yeah, I mean, I would just do them again and again and again until you hear the angels singing. Eventually,
Gotcha.
that's what happens. I mean, you just keep on writing it out. It's the only thing that can make the angels sing, by the way, is putting pen to paper. The angels don't sing.
Though, so I feel a little bit more confident when
Look, the angels won't sing. They won't.
I know. I'm gonna.
They'll stay silent. They'll sit there like this. But eventually, you'll hear them. First of all, they start out. They go you do begin to hear them initially, and then that sort of encourages you, and then suddenly it's a whole chorus of angels. It's a beautiful thing. It is. A lot of people here have heard angels singing. They have.
I have a question.
Yes, Mariam.
So can you go back to that file that you were just showing us?
The file I was just showing you, maybe. I think I might have deleted it, but I'll bring it back up. Yes.
Okay, so you see how the answers for question 1 shows which OH goes to which attacks which carbon. But isn't it for the fuse, they're kind of the one that is closer goes to the further one?
Well, actually, let's run a little experiment here, Mariam.
Okay.
Let's go the other way and see what sizes the rings are. Right? So let's pretend that this OH was attacking the other C double bond O. Just for kicks, right? Just for kicks. 1, 2, 3, 4, 5, 6, 7, 8. So that would be an 8-membered ring. And 1, 2, 3, 4, 5. And that'd be a 5-membered ring. So what we actually have here is a 7-6 system as opposed to an 8-5 system. So I was able to, but they're both going to give fused rings, by the way, in this instance. But you can see that it was important here to be mindful of which OH was going to attack which C double bond O, and we can tell that by the size of the rings in this instance.
Why would they both get fused rings?
Thank you.
Because they have a common bond joining the two C double bond O's together. This one.
So it's not always the case that if
No. It's more. It's an all poodles are dogs, not all dogs are poodles type situation.
So the easiest way to solve this would just go to the complete answer and then count it all out. It'd be
Yeah.
like 1, 2, 3, 4,
Yep.
5, and
Count the
number
rings.
it out. Yeah.
Count the ring sizes. Make sure you're getting each OH. That's the only way to really be sure, right?
Yes.
In other cases, I mean, you've seen other examples that I've shown you, where it's possible. Like for example, well, I think it's this one. Wonder what this one would do.
So you would start number 3 is the one you're looking at?
Yeah, I'm looking at number 3. I'm just trying to see if it would give a fused. Yeah, I think that'd give a fused ring as well. Whereas this one, I'm trying to see. Yeah, that one would probably give fused rings too.
I was going to say, yeah.
Yeah, I think I think what I've done here deliberately is chosen examples that where you really had to be mindful of the ring size. But they were all situations where something was joined with a common bond, and that's the reason we're getting all fused rings here. So I guess I need to kind of adjust things a little bit. What I can say is that there are going to be situations where it's obvious where they're going to be separated rings, and those will always be the way they're going to be. But there are going to be situations where you can get fused rings by switching which OH reacts with which C double bond O. And for that instance, you've really got to be very certain that you're getting the right ring size for the product that you have in front of you. So I might have to do a little adjusting there as far as my the way I explain that.
So would it be safe to say that you should just count the ring size first?
Yes, Julie.
Yeah,
yes.
that was what I was trying to say. You should always start by counting the ring size and then going from the OH to bond.
I think that's excellent advice.
Okay.
I do. All right. Any other questions? So that's what question 2 is going to look like. So question 3, I'm actually going to be real generous here with question 3. Real generous. Real generous. With question 3, I always choose something that is a hydrolysis reaction that has a basic kind of mechanism of something that ends up becoming a carboxylic acid. So one of the products here is always a carboxylic acid. I always make it a carboxylic acid. It's a secret here. All right, so let's go ahead and follow the mechanism. That they all, even though they all start with something a little different, they all have the same kind of thing going on. So I'm going to go through this one. So the mechanism for question 3 is always a basic kind of mechanism, but I always make it something that has a little wrinkle to it, and you'll see that wrinkle in a second. So hopefully you've watched the videos for the weeks I told you to, and if you have, then you would have already seen this, but some of you haven't, so I suppose I'm doing it for your benefit here. So the first step is going to be the OH minus coming in, attacking the C double bond O. And then the negative charge comes down and kicks out the leaving group. Oops. Now this is where the wrinkle comes into play. Because, you know, when you've got to this point, you think, oh, okay, well, look, I've already got my carboxylic acid here, and all that's really needed is this NH2. And you're thinking, okay, I've got an N minus here. That's just going to take the H plus in the second step, this one here. And you think, oh yeah, I'm good. I'm done. You know, I'm crazy. I can go for it. No, you can't. Now the reason for that is because at this point you've formed a carboxylic acid and it's in a basic environment. It's got OH minus. We've also got this N minus here. So what actually happens is that the N minus will take the H off the OH. Oops, that's not very pretty. And we end up getting this. So there's your NH2. And there's an O negative now. So this is a carboxylic acid, which means that it's an acid. The H plus is easily lost because this negative charge can be stabilized by resonance between the two O's. The N minus here can't be. That's what makes the O minus more stable here, pretty much. And then that is what produces the carboxylic acid at the end. So what you're going to get is always going to be something that does that. All right, does anybody have any questions? I recommend for you to understand that a bit better, if you haven't already done so, to watch certain videos, and those would be this one, reactions of acid anhydrides, hydrolysis, basically anything that's got reactions and hydrolysis in it. Yeah, reactions of esters, hydrolysis, especially with base. Yeah, hydrolysis, base, anything that's got hydrolysis and base in it. Lactone hydrolysis. More about hydrolysis with base, I suppose. Here we go. Hydrolysis, base. There's more. You have to hit load more to get more videos. Yeah. I've also got a video here, common mechanistic patterns for test 3, acid, basic, neutral. Oh, reaction. I did have it. Wow. You know what? Julie, was it you who was saying this?
Yep.
You're not crazy.
Thanks.
Thank you, Julie. You're not crazy. Oh, and look at that. I even have a what to expect for test 3. Oh, isn't that cool? I see. I'd forgotten I had all this stuff. Whoa. Oh, nuts here. Crazy. All right. So how do you access that? Well, let me go back to test 3. There's a little bit of a wrinkle here too. It's a good thing you turned up today, folks. All right. So you'll notice that you get the mini lectures, and here's the thing. There's so many of them that it actually doesn't put it on the one page. There's this little button at the bottom that says load more. You actually have to hit that to get the other ones. Can I get an idea? How many people... Let me see. I'll see if I can do a... Okay, I'm going to do a poll here. I need to know this. Poll. polling. Stop sharing. Edit. I'm going to do a new poll here. Did you know about the videos I just mentioned? And it's completely anonymous. Yes or no? Because I want to know how many people knew to do that or didn't know how to do it. This will be good for the future.
Dr. Musgrave, are you talking about the ones that were past the load more, or
yes,
just these
yes. The ones that were passed for load more. Okay, that's what I want to know. The ones that were passed to load more. Did you know about them or not? Did you know about the ones passed for load more or not? 5 seconds. 4, 3, 2, 1. Yeah, a lot of people didn't. There you go. But now you do, right? I'm not inclined to send an email out about it either, because people who attend the lectures need to get something. And of course, anybody who's watching the lecture who didn't attend, they'll get this too, obviously. But anybody who doesn't bother to either attend lecture or watch the lecture at some point ain't going to see nothing. But anyway, there you go. All right, so you know about this. This is interesting. So this is a good video. I like this one. And the reaction classifications, I've already done that, by the way. I went through and did that in one of the other lectures. I'd forgotten I had done this video, to be honest. And then there's what to expect for test 3. I think that's useful too. Yeah, that is useful. Good stuff. All right, let's talk about the NMR and functional groups. I do have a video for that too, though. That's kind of cool. All right, let's take a squiz at what I'm talking about here. With this test, we're getting a synthesis question. This synthesis question, I guarantee, can be done with reactions from question 1. It's only going to be a 2-step reaction, meaning there's going to be one intermediate, and you'll be trying to figure out what those are. And this is going to follow a similar method to what we used in test 2 in order to solve those kinds of problems. On the review day, I'll be going through a whole test, and you'll be able to see me do one of these in action, but it's going to be very similar to what you saw in test 2. All right. Again, we're not out of the woods here yet with the NMR. So there's going to be an NMR problem here. And what I wanted to point out here, and I've got this in the video, but I'll point it out here as well. See if I can. No, it won't let me. That's weird. All right. I'll have to do it here. That's okay. When we look at the formulas of different functional groups, a carboxylic acid will always be CXHY, and I'm going to be try and be real general about this, O2. Let's see what's next. The chloride, acid chloride. Oops. We have a chat problem here. Is he going to review question 4? No, he isn't. Because it's very similar to the synthesis question you did in test 2, Sylvia. But I mean, I will do one when I do a review. I don't know if that's a satisfactory enough answer for you, though. Is it, Sylvia? Okay. Okay, if it's an acid chloride, it'll be CXHYCOCl. So you notice how you're always given the formula as part of the NMR? If it's an acid anhydride, it'll be CXHYO3. And let's see, if it's ester, it'll be the same as a carboxylic acid. And if it's an amide, and nitrile. So what I'm saying here is that if you know what the formula is, then there are certain things that you already know what you're going to get. Now, if it is an O2 formula like this, you want to be able to tell if it's a carboxylic acid or an ester because they have the same, right? I'll just check mark on those. They're the same. But for the carboxylic acid, that'll have a 1H at about 10 to 12 ppm. For the OH, whereas the ester won't. So that's how you'll be able to tell the difference. Any questions? All right. So just about the this is only about whether you understand about the relationship between functional groups and the molecular formula for the NMR problem, not about the NMR problem itself, all right? So tell me, oops, let's try this again. Okay, there we go. So the relationship between the functional groups and the molecular formula. 5, 4, 3, 2, 1, 0. All right. So 15 to 2. Anybody have any questions that could help them here at this point? Any questions? Okay. Now the other thing you'll get here is a roadmap problem. And I've already heard from some students, they don't like these very much. But, well, they are what they are, I guess. You do have to know the reactions. Now, what I can tell you is that it's not necessarily going to be so that you can get much information off question 1, although there might be some reactions in question 1 that might be able to help you. So just keep that in mind when you're going ahead and doing these. And, you know, I'm going to spend some quality time reviewing these on Tuesday, I think. I'll go through a whole bunch of them on Tuesday and show you some tricks and some things in order to help you get the answers right here, not just in this question, but in other questions on the test as well. This can be very helpful, okay? So I'd like to do that that's what I'd like to do on Tuesday. Let me see what else I want to do today. So we've got question 4, question 3, question 2, question 1. All right, okay. Well, in the last 10 minutes, Sylvia, out of respect for your question, I'll go ahead and do question 4 from this test. Now I'm going to need the key for this one. So that's what I'm going to go ahead and get. This is spring 2017. All right, you're welcome. Don't say I don't do anything for you. All right, keys, spring 2017. All right. All right, so again, the problem here that we're being faced with is this one. I'm not showing the answer, obviously. I want to show you how you would get to it using question 1. Okay. So the setup for this one we know is going to look something like this. So A, B, and then C. And that's what you're looking for. You're looking for this A, B, and C. So what I'm going to pretend is that you did question 1, you did it correctly. So what I'm going to do first is I'm going to look for something in question 1 that has a similar functional group to what we're seeing here in the product. So always look at the product first, right? So let's look at the product first here. And I'm going to start in question 1 and look for something that forms a similar, oh, look, there he is right there. Look at that. And there's the reaction. And this is kind of tricky. Because we need to work with analogy here a little bit. Not analogy, analogy. So this is the thing. If I know that this plus SOCl2 gives this Cl compound, what I'm trying to figure out is what compound would have produced this acid chloride. Now it's still going to be SOCl2 that does the same thing. So that's how I know that that's SOCl2. I've got to figure out this B compound here. And what I would want you to see is the pattern is that the OH gets replaced with the Cl. So I know that B would have to be this. Okay, so that would have to be B. Now, gingerly, I'm going to ask this. I'll run a poll here. I don't think looking at it now, I'm wondering if I'm going to get a good answer or not, but we'll see. Right. How do you feel so far about it? I'll give you another 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. There we go. It's kind of what I expected. Although there is one, I have no idea what's going on. That's a little bit disturbing. Can anybody ask a question that would help here?
Are you working backwards at this point?
I am. Yeah, because, well, what I know is I know that from this reaction, I know that to get a C double bond OCl compound, I need SOCl2 on the arrow and a carboxylic acid as the reactant. So that's how I know that just looking at the pattern going from the OH to the Cl, that I'm kind of working backwards and saying, well, this must have been the same thing except with OH for the Cl. Does anybody have any questions that could help here? Any questions?
How did you get from B to A?
I haven't gotten A yet.
Oh,
All I've gotten is B and C at this point, Miriam. All right, any other questions? All right, now to get to A, I'm going to need a reaction that starts with an acid anhydride and goes to a carboxylic acid. See if I can find that here. Acid anhydride to a carboxylic acid. And there we go, this one here. So based on that, I can see that it's going to require the same reagents. So A is going to be whatever I see here, 1 H2O, oops, OH minus, and 2 H plus. And that would complete the problem. But the key part is the part where I got B. And that's really what I want to focus on here. So just so I know, because I will do more on this if people want me to, how do you feel about how I got B? How do you feel about how I got B? How do you feel about how I got B? I'll give you another 5 seconds. 5, 4, 3, 2, 1. Okay. Good. At least more than 2/3 of you get that. That's good. Now the other 4 of you, I'm not leaving you out in the cold. I'll do another example of these on Tuesday, along with some of those roadmap problems as well. That'll pretty much round things out. But as for the actual mechanisms and the reactions, you're best off for studying. The best method is to, actually I don't want that. The best method is to do these problems that are at the end of the blue book here, starting on page 22, the blue book, or 20, I don't know, the page is misnumbered here. But anyway, this page here, that's got the problems on it, and do those problems, do the mechanisms, and then compare those mechanisms against this file that's in the test 3 folder. And what I'm talking about is this file, test 3 mechanisms. That's going to be the best way. Don't use flashcards. It's not going to be helpful to you. And there's all the mechanisms for all 57 problems. 1 per page. And that's by far the best way. Now, a lot of people are going to be tempted to try and shortcut it. Oh, I don't want to spend that much time doing it. Well, you either want to pass or you want to fail. So make up your mind, do what you need to do. To be blunt, that's what's going to have to happen. All right. Well, on that note, I think I'll say goodbye, and I'll see you all on Tuesday.
Thank you.
Thank you.
Thank you.
Thank you. Tuesday.
thank you.
See you Tuesday.
Thank you.